Okej. I teraz jeszcze, żeby to działało. O. Okay. Looks like it's working. So, hello everyone. I'm very happy to be here in Poznań. It's actually my first time to be in the city, and I've enjoyed it so far despite the scorching heat. But yeah, it looks nice. So, my name is Marcin Szymczak, and today I would like to share my story, which I titled, When Does My Bus Leave? And it's a story about laziness, and at the same time, I hope I could inspire you to kind of think outside of the box and inside some constraints you could be set upon yourself. And the subtitle is Parsing JSON Documents in Resource-Constrained Embedded Devices, because this is precisely what I beset to do, although this talk will mostly focus, it would be a story of how could you yourself write a parser library that is applicable to this specific scenario, which I hope is interesting because of the requirements. So moving forward, I'm open to work. If anyone's hiring for a senior Rust developer, then definitely reach me out. I have 8 years of experience, mainly C++, C, Python, outside of Rust, of course. Professionally, I've been working with this language for 4 years, but to be honest, I'm very passionate about the technology since its inception, which, as Rafał some time ago on Rust Poland meetup described, it's not an easy thing to define because there are multiple dates of when Rust has been developed. But yeah, I've been into it, let's say, since 2014 at least. Yeah, and I do truly think it's the future of the industry, basically. So yeah, the agenda of the talk, I hope it's pretty simple. First, I'll talk you about the idea. I tell you about the idea I have. Then I'll touch very briefly upon Rust in embedded systems. And the reason is because of it's directly connected to my idea. But what I really intend to do here is maybe just to tell you what I found out and how I truly enjoy writing embedded Rust compared to embedded in other programming languages. Then we'll talk a little bit about parsing. Then we'll dive really deep into the implementation, which I hope would be easy to follow. And yeah, sorry for the fifth heading. It shouldn't be here, but basically it's the same. And then I'll jump into some conclusions, because along the way, I found some cool compiler optimizations that can happen, and some cool tricks which you can utilize to basically make your code either faster or with a smaller memory footprint, etc. Yeah, and what you can expect is there's going to be lots of code samples. This talk is more kind of, let's say, hands-on, despite no one's going to be coding. I want to tell you a little bit about macros. I know those can seem scary sometimes. We're just going to use them for a specific purpose, and that's all I'm going to tell, how I'm going to talk about them, and cool compiler optimizations, as I told before. So the idea, it's actually quite simple. I wanted an all-in-one solution which I could stick on my fridge, and it would tell me when does my bus leave. Because I have a bus stop right beside my flat, it's very near, but the bus leaves very rarely, so once every hour or so. And typically, when I take time to, check when it's gonna leave, it's either too far ahead or it just left. And I thought it would be cool if I could have this device, stick it on my fridge, just look up the timetable, and then know if I should be heading for the bus or for the tram. What I wanted to do is I also wanted this in the sense of all-in-one solution. I had a Raspberry Pico, and I wanted to do the whole job. I didn't want to do any kind of client server where I could parse something or maybe optimize the data, because this is a very constrained device. I wanted to do it all, and turtles all the way down means I want to do it all in Rust, whatever I'll be doing. Bonus points for low power usage, but as it's gonna be inside my home, it shouldn't be a problem to charge it every now and then. But yeah, I want to be kind of efficient. So briefly on the embedded Rust. For me, this is a breath of fresh air because typically when I was working with embedded, let's say in C or C++, it's all kind of re-implementing the same old stuff, or very rarely I can find a good documentation on, let's say, the SDK, which I have to use, etc. Especially when it comes to third-party libraries. So the typical scenario which I found is there is some kind of huge framework which implements everything for you, you can use it, but if there is something else you need, it's hard, or the code written, like all the libraries might not really have that in mind to be on resource-constrained devices, so you can't use the library, or it's inefficient to do so. So for me, when I looked up, crates.io for some embedded stuff, I was amazed. So I had this e-ink display. There's already a driver for that. I have this Raspberry Pico. There is a hardware abstraction layers which basically make it cross-compatible. If you want to contribute a driver, you can just do so. You don't need to worry too much what kind of device that's going to run on. And it's great because you get pretty much the same experience as you are typically used to in Rust for embedded devices, which is known to be, let's say, trickier to work with. And yeah, so harness the power of the ecosystem. And if you were to try out embedded Rust, please try searching in crates.io first, because you're going to be amazed what you can find. Yeah, and for embedded, there is a great framework or library called Embassy, and it's for embedded asynchronous software, basically. And it kind of gives you the async await of Rust in embedded world with no additional craft. So what you get is you have it abstracted over all of those devices which I mentioned. I pulled it from the GitHub, probably it's even longer now. It gives you all the familiar types from standard library, some very easy support for timers, and it's real-time ready, as I described. So you create your async tasks. You can have multiple executors with different priorities to preempt each other. But I think the best thing about it is typically when you have like a critical section, you have some interrupt handling code, etc. You really have to treat it as a multi-threaded code. Despite the chip might not even have more than one core, you really do have to think about it. And Embassy basically puts it as like a first-class citizen. So you cannot easily mutate global state without proper locking, mutexes, etc. So it already eliminates a wide class of issues you might encounter. At the same time, the connectivity is there. If something's missing, you can easily use it because actually you can easily add it, because Embassy actually makes use of some already existing no-STD compliant libraries, and you can swap for your own. It's pretty easy because of all the hardware abstracting going on in the Rust ecosystem. Yeah. And moving forward, I just wanted to show you some kind of sneak peek of how would it work on Raspberry Pico. So as you can see, we just initialize the Raspberry Pico, let's say, take a pin, and in the loop, we can set it high, wait some time, set it low. And at the same time, you can see we're doing some logging. There's a fantastic library for Rust called DFMT, like the third formatting. And it's responsible for helping you to debug your code, to send over those debug messages. But the cool thing about it, it's not actually sending the whole string. So it's really optimized. It builds a lookup table, and the let on could be on index 1, let's say, let off index 2, and those are just the numbers that's going to be sent over the wire. While you're looking at it in your terminal, it's translated behind the scenes. So you have the pretty human-readable message, but it's really cheap in terms of to send it. At the same time, if there are some parameters, because it supports the usual formatting you're used to, it's also going to do some tricky serialization just to send whatever, like the minimum value that is needed. But I've been talking about async Rust, right? So let me show you. Also, it's pulled from the GitHub. Another example. So here we have a task called toggle let, and when you create it, you specify some duration. And we'll be toggling the let again, but we're waiting some specific duration. Sorry, I have a pointer. So we're waiting specific duration. And in the main, in your main, we're basically able to spawn, for example, 2 of those tasks with different durations. They will be interspersed, and as you can see, they do locking, so it is impossible for them to access the same state at the same time. It's perfectly synchronized, let's say. One or the other will have to wait for each other if they happen to coincide. And for me, the coolest thing about it, because we're going willy-nilly here spawning some tasks, but what's actually happening behind the scenes is this embassy is able to calculate the amount of stack space and task space and basically bake it into your program. So this function, instantiated twice, is gonna take precisely this amount of space, known statically on nightly compiler. So it's not a dynamic allocation, and it's not allocating some kind of buffer in memory in which you hope it will fit. It will fit exactly and use no more memory than is precisely needed, which I think is very cool. Okay, so far so good. I have my idea, I want to implement it. Wi-Fi worked on the first try, I'm connected. Making web requests is also very simple. I just await on the requests as you would use requests in typical application. But then, unfortunately, I hit a huge roadblock. So I need to figure out the stop ID of my stop, because what I want to do at the same time, I don't want to be hard coding any kind of IDs, any tricky stuff. In my code, the most I'm willing to put is the name of my stop, and let it figure it out. So I need to query all stops. The JSON containing all of this information, so basically all stops in Gdańsk, is 684 kilobytes. Raspberry Pi has only 264 kilobytes of RAM. There is no way I'm gonna fit this JSON for processing and basically go forward with that. I have to come up with some solution. So what did I do? Sorry, just let me show you the schema. It's actually pretty simple. It's just a lot of data in this JSON. And I want to find the stop ID when the name matches basically the stop I expect. Okay, so my requirements for that are no STD support, obviously. Although, to be honest, this can come with an asterisk because Embassy supports dynamic allocation, etc. It kind of allows you to use the standard libraries. So if you use something not really supporting no STD, it may work, actually. Yeah, and what I really need, I don't need to parse the whole JSON. I don't need all of the values, etc. Ideally, I want to match on it somehow. So search for in the stops, find the name of my stop, and extract its stop ID. So maybe there is a library that can help me. So I looked into the ecosystem. And unfortunately, at the time, I came up with the project because I believe the things have changed now. There was no such thing because all the SERD and derivatives, they gave me all of the values alongside with parsing the JSON, and I really wanted, they didn't support streaming first of all, and I really didn't want it to read all of the different values. Then I found some querying libraries, and they also required, for example, to get the whole JSON because this document is not really streaming friendly, right? You have to get it all to validate it, for example. So I'm willing to take the assumption the JSON coming back from the API is valid, but that's not necessary for the libraries. So I turned into last resort. There are great parser combinator libraries, winnow, nom, and chumsky, which basically allow you to compose your own parser based on some kind of combinators, as in the name. So take at least either this or that, etc. Some atoms, and you basically make your own parser. So I thought, cool, implementing JSON shouldn't be too hard, right? So I just used them. And I believe this is where the change happened. So I think winnow now supports kind of streaming, parsing, etc. But it didn't at that time. So I thought to myself, I could just budget, right? Let's just look for the string in the stream. The ID is gonna be around somewhere, either further down the line or before. I can look for matching brackets, etc. But would that be fun? I don't think so. Although I would have had my solution and I would know when my bus leaves. Because spoiler, I do not know up to this date. Yeah, so it looks like I need to create my own parser. How about creating my own parser library? I could make the special case of this library, like the usage of it actually, to be parsing JSON. I want to make, let's make it right. So I want to make a new parsing library that's kind of generic. I love the combinators approach, so let's take inspiration from that. And what I want to focus on is not transforming the data, so basically parsing it, although this is a parser library, but I want to kind of support matching on the data. I want to support streaming in the data and taking just what I need and as much as I need. So my ideal workflow for this parser is I get some chunk of JSON, I move forward with it, then as this data is consumed, I could request some more and then put it to the parser. So it's kind of jumping on the Sans.io bandwagon you probably heard about or not. So basically the input, the library is agnostic to input, right? So you kind of handle it. The library just tells you, I need some more, or there was an error, or you should move back, I don't know, 10 bytes, give me some more data altogether, and it should figure it out. So yeah, so I figured in this loop we could be putting the data into the library, have it parse it, and not really extracting any data until it finds what it needs, and then it should just return a result, right? Some kind of, sorry, not some kind of, the actual stop ID I needed. So let's make it lean. What I also wanted to achieve is to kind of have the very similar memory usage or efficiency as if you were to handwrite your parser. So if we were to think of like a giant state machine, you could do yourself using an enum and a match statement in a loop and figure out where you are, what you're passing, etc. I wanted to make it easy to compose such parser instead of doing it by hand, but not to be excessive in terms of memory usage, so the additional state. And yeah, this I mentioned already, so I took huge inspiration from already existing craze, but I adapted it to my own needs. And JSON is just now a use case for my library, not its very purpose. So moving from like the beginning idea, I'm now knee-deep into implementing some library that my solution is actually just a use case for. And what I wanted to do, of course, is to keep it no STD, but at the same time, I wanted to test it every time, basically, I build. So I kept the standard library just for tests, while building it for release, etc. I want to make sure I don't use standard library, so you can pop this attribute in your crate, and it will basically ensure it for you. So, and one more thing is that if the library shall ever support having STD, it should be a feature that opts you into standard library support. It's because the Rust features should be additive. They shouldn't take away stuff, so there shouldn't be a feature called no STD. It's the other way around. Okay, so let's jump into the implementation. What do we need in terms of it? I figured first let's define how I'm gonna get the data. What type of input do I have? So we can have a trait that just gives us the next character. It should be fine, although with moving along with that, I found out that there are some additional methods I'd like to have, although I want to keep it as simple as I can. So I've added pick because it's useful to pick at the next character in the stream, but not necessarily extract it. And sometimes my combinators require kind of rewinding. So I also make the trait have to support kind of getting the current state of the input, which basically is either, I don't know, an offset into the buffer, etc., and some means to go back to the previously saved state. So those are the two methods. I will talk about it later, probably. And then I also needed to define a parser. And for me, ideally, like in the simplest terms, it's just something that I can call parse on. With the input, it gives me a result. What's special about my library is this state, unknown, because typical parser libraries can give you that they accept, especially the combinators. So specific combinator can either accept input or reject it. While rejecting is not necessarily an error, because if you're parsing, I don't know, true or false, so the first parser can say, I reject it because it's false, for example. So this is a very useful piece of information, not necessarily an error, but sometimes there are situations where parsing can result in an error. Let's say a string was never closed. This is an error, a type of error. Yeah, and my parsers also support saying unknown. And this basically means I don't have enough data to make up my mind. Please give me more data. And realistically speaking, I needed to add some more detail here just to make it workable. So I've added a function to reset parser state. When designing the library, I really kept the state as small as possible because it really simplifies things, which I'm going to talk about. But I also needed to add the amount of characters that were consumed by the arriving at the subsequent result. Why does it matter? Because if parser returns accept with some amount of data, that means it consumed it successfully. So you can just discard them and ask for more. If it rejects some amount of data, you need to rewind your buffer when having this sort of loop of getting the data and sending data to parser. You have to rewind it a little bit because it's sometimes impossible in the design of those combinators to have it handled for you. And then if the same goes with unknown, so it took some data, took a little bit too much data to make up its mind, you have to rewind it. And for error, I don't think this is really recoverable, but I just provide this information just in case. Okay, so let's create the first, let's say, piece of the puzzle, the first parser of this library together. So I figured the easiest thing to do was to parse a literal, right? So you'll give it some string, and then it should expect the very same string at the input. This is how the struct would look like. Why it's a struct? Initially, I thought I'm gonna be cool and just use closures everywhere. So my closures were implementing the parser trait. I could have the data be just a moved in state into the closure. But it turns out if you nest it like, I don't know, tenfold, etc., the compilation times really blows up. And when I tried to print out all of the types in my program, it went to like gigabytes of data because each closure is anonymous, but it has unique name. And when you nest them, it's kind of combined. And when you nest them multiple times, multiple fold, it just blows up so hard. And by having named structs, you just avoid this problem. It's way faster for Rust compiler to reason about them, and they are not anonymous, and it really helps the compile times sometimes. Okay, so how would it look like to parse a specific literal? So keep in mind we're in the impl block of this struct. So we know the literal we want to parse. We just iterate for the chars that we expect. If by picking into the input we find some char and it is different than what we expect, we just return reject with the count of characters we just consumed. This is helpful for the, let's say, outside loop. If not, we just continue on, and calling this next basically consumes the character we just picked into. And if we don't have any character to read, we have to return unknown, because if the literal is longer than the input currently is, we just cannot make up our own mind. And if that all passes, we just accept the input. And a simple test for that would look like this. And I believe this is self-explanatory. Yeah, but what's really cool about that, developing this library alongside populating with tests is really great, because they are easy to come up with when you're dealing with parser library, and it's really helpful for regressions. Yeah, so let's maybe step it up a little. We have a parser that can parse specific things, but the true power will come if we will be able to combine the parsers somehow. So maybe we can parse a specific literal or the other. So for this one, we could create an either combinator, and it would do exactly what I told you. So it will just try one parser. If it fails, rewind the input and try the other one. This would be the implementation. I think there's nothing surprising here in the sense that first we try the parser named A, which is the first one. whatever it returns, that's, let's say, decisive, then we return it immediately, and if not, we move back the input which we saved here and just return whatever the second parser returns. And this actually allows us to combine two parsers. So here is a test for that. Maybe I can just show you one more thing. For all of those parsers, just create some helper functions to make it easier to create them. Yeah, so we create a parser that either parses foo or bar, and this works as intended. And this might sound like not much, right? But behold, the power of parser combinators actually provided us with the ability to parse a small subset of JSON, which is the Boolean, right? So this is an example. Let's move on then. We're catching up speed. Let's see how implementing a subset of JSON grammar would look like. What we're going to be focusing on here, as you might expect, is whatever I've needed to parse this specific JSON I had. So this is basically how a JSON parser, so JSON syntax looks like. And implementing it with parser combinators actually allows us to kind of represent the very same thing in a similar way, but in code. Let's imagine, because we don't have this for now, that we have a parser combinator called alt that just tries the alternatives which we list inside. And our JSON value can be either a string or number, object, array, true, false, null, which is here. I think it's beautiful to look at it this way, because with the parser combinators, you can really describe the problem you have in those understandable small logical bits and pieces, and they come together to achieve your expected outcome. So yeah, out of the whole grammar, we are now able to parse null. We just have literal for null and Boolean. Let's step it up a little bit. Let's try parsing strings. Parsing strings would be easy if you were to have two additional combinators. You see where this is getting. We're going to look at how to implement them. So imagine we have a parser combinator that just has to use the parsers in sequence, a chain. They cannot fail. If any of them fail, basically the whole chain fails. And if we had such parser, and additionally, if you had a parser that would be consuming its input as long as predicate is true, we could create a parser for string, because keep in mind, right now we're only interested in going through the data in the, let's say, in a structured way. So we don't really need to know what this input is. It's a string and we can go through it. So let's see how the take implementation could look like. So again, a simple struct with a predicate I called f and a helper function to create it. And now the implementation. It's all kind of similar to each other. So we also keep the count, but now instead of comparing it to something, we just have to call predicate on every byte we can pick into, and then increase the count, go to the next one. As you can see, this parser actually never rejects, right? Because if the predicate is false, it just thinks, okay, I consumed, for example, 0 bytes. And for now, it's fine. Yeah, a simple test for that, it just returns the count of the ASCII white space. But there is another parser combinator that we need, that we direly need, and it actually is very tricky to implement. So I told you about the chain, right? So we want to link however much parsers we want in a chain, have it go through them one by one, and finish only when all of them succeed. So what I would like is just to use a tuple, right? I can use a tuple of however many parser I can provide, and it should just do its work. But it turns out that creating an impl for like an arbitrary size tuple is impossible currently in Rust. Typical frameworks work around this issue by just generating the code up to some number of items in the tuple, and we're gonna take the same approach, although I want to show you how to do it. So at least, let's say, using macros for such a simple tasks will not be daunting, if it is for anyone. Yeah, so basically we'll implement up to size n, and it's up to us however many macro invocations we'll create to just achieve our goal. But first, we need to understand what the macro needs to do, right? So is there a pattern to implementing the chain that we can take advantage of? So basically, implementing this chain, I'll just go back a little bit, it should look like this. We have the tuple of parsers and state, which is basically an index into the tuple, right? Tuple. So if it's 0, we try the first one. If it's 1, we try the second, etc. And when it's finished, we just know we are done. So it looks like we could create a code like this. So first, we could destructure the tuple into variables named in the same way as types. That's gonna be useful later. And then just match on the state, right? If it's 0, we try A. If there were another parser here and the state would be 1, we tried B, etc., etc. So there is a clear pattern here. Here I'm showing for binary tuple, and here is, let's say, just the diff, or what is generically added here. So we just need this little bit of code to be repeated as many times as we need. So let's see, like, how does macro rules work? So macro rules 101. Macros in Rust, at least the macro rules specifically, is a type of kind of pattern matching code generating mechanism. It is quite limited, but at the same time, I think it is very useful if you actually arrive at the situation where this is the right tool, because the nicer macros, which make use of syn, are very heavy in terms of compilation time, and for example, Serday makes a lot of use for it because it allows you to derive deserialize or serialize. It's greatly useful. I mean, I can't imagine my life without that, but at the same time, it comes at a significant increase in compilation time. Macro rules are simple, and they're pretty fast. Although I do believe they are getting compiled to some separate crate under the hood and then executed. But anyway, so what I would like to see is a macro that I provide a set of identifiers to this macro because they cannot come up with their own. So whatever you pass to macro, you can, let's say, use in your output, but it cannot join identifiers, split them, etc. So at the very least, we would have to provide a list of letters, and those letters would represent to the arity of the tuple and be used in the implementation, especially at this destructuring stage. So this could be those letters. But to make our life easier, we need to uglify the macro invocation a little bit. I try to give it some structure. So first of all, we cannot really count like when processing this specific arity, so we need to provide it. So 0 is A. I additionally make use of this IA, which I'll talk about at the end of the presentation a little bit, but let's say this is for convenience, trust me. Yeah, so basically this is how our macro invocation would look like, and now we want to implement it, right? So how do we do it? Macro rules is simple in principle, although hard to read, and can be a little bit clunky to make sense of what's going on. But basically, you come up with some patterns which are actually matched for here with the arguments to your macro, and if it matches, it outputs the body. As arguments, you can have like a single literal, or basically anything, docstring, comment, whatever, if it matches, and then you can transform it somehow. Additionally, what's going to be greatly helpful for us, in macro rules, you can match for some repeated patterns. So for example, as you can see here, we would like to match for some number literal or just literal, specifically this type of fat arrow, but it's, let's say, not magical in any way, I just made it up, and some identifiers which you can use as type names or variable names. So this is how the pattern would look like. And then we could instantiate a single branch of this match, which you have seen before. Maybe I just come back a little bit. So we could instantiate this one and recursively call our macro with the rest of the identifiers, right? Or alternatively, we could perhaps expand all of the identifiers which we had, because there are different options you can take. Yeah, so just a simple macro to show you around in terms of the repetitions. It's really ugly to read, but it looks like this. This $T is just the name, like for the variable, macro variable that I came up with. The type is basically its type, and those are like kind of syntax items, so it can be identifier, literal, etc. And that would be it. But I want to have any number of identifiers which I'm inside of them named T. So I wrap it with another $, and comma plus means they will be comma separated, and there are at least one and more. And then this kind of invocation would result in, would give us this, because what we're doing is kind of expanding the very same list which we match for, so not transforming in any way. Can be boring, but it's a good first step. Because with that in mind, we can do anything here around this $T, and it will just be output alongside. So we could perhaps have an impl block with the type of code we just seen, and for inside those parentheses, we could structure it in such a way that it will give us the match arm that handles this specific parser. So I used an avocado to make it more readable. So here is avocado is a single single name or letter. So we would like to have an impl where we have all of the parsers with each of their letters, because this is in parentheses, and my specific parse function should be filled in. So for now, let's say in this state where I just have the to do, if I expand this macro, it just gives us the same thing 3 times, but each time, as you can see, the letters are all there, right? Okay, so then how does the macro look like? I actually omitted the macro rules and pattern matching to fit it in the slide, but as you can see, this is a very similar structure which I showed you for unary tuple, unary, so like with the single item, but I've included this macro expansion here. So here, in the very same way, we are destructuring the tuple into variables of the same name as the type names. It's just to reference them somehow. And then inside the match statement, we have another expansion. So this is going to repeat a couple of times, each time with different I, which were the numbers, so the indices, and with a different T, which are the letters. And this basically gives us the ability to come up with this incantation and have the chain implemented for, I think, 12 array tuple, right? I think I don't 12 here, yeah. But you can go as far as you want, although it is bounded. Yeah, so now it seems we have everything we need to parse the string. So, yeah, and this is the test. These are the t-tests, but those I think you can expect. I'm gonna move on a little bit to numbers. So for them, I took a really small subset of JSON spec. What I wanted, because frankly speaking, in this JSON with stops, I can sometimes see fractional numbers, but definitely not negative numbers. So I just focused on describing that. So let's see, the parser for number could look like this. In sequence, so chain, we would like to take at least 1 digit. For the take at least, we didn't see it before, but imagine this is the same parser we implemented, take, but which conditionally has to match at least some amount of time for it to be successful, because the one we've just implemented, let's say, was happy even with 0 amount of input consumed. And then on top of that, imagine it's just a const variable. So we don't store the counts anywhere. It's kind of baked into the parser. So this is a parser that takes at least 1 digit. And if that's the case, we could also optionally take literal dot and at least one digit. And this basically describes numbers for us, but it is pretty inaccurate because, for example, those could be all zeros, etc. But I just went with it for simplicity. Yeah, so what we need, we almost have everything. We just need to figure out how to implement opt, right? So this should be a parser combinator that optionally uses its internal parser. Otherwise, it also should be happy, so it should accept the input in either way. So a simple struct with the parser as a field, and the implementation is just this. So we take the input, this is input state, it is very important not to forget about it, and try out the parser. And if it accepts, then great. If it doesn't, we restore the input as if nothing happened and return the fact that we actually accepted this input. And this is very powerful because despite being so simple, I mean in terms of lines of code and implementation, along with other combinators, it allows us to create, let's say, sophisticated mechanisms, right? Because the opt is pretty, let's say, it is unaware what's going on inside. And here we're describing this complex logic, right? Chain of parsers, there has to be literal, and then maybe one or more digit, etc. And it's all just achieved just by combining those combinators. Yeah, and a test for that, as expected. It looks like we can now parse most of JSON. We just need to focus on objects and arrays. And this can be daunting at first because those are the composite, let's say, composite types, and there can be any number of fields in an object, etc., etc. But it turns out that it can be straightforward to describe if we have the right tools, of course, right? So an array is just a literal opening it, and then imagine we had the parser combinator that just tries out its parser and it expects another one separating them. So it tries this one first and then expects this one, then goes back to this, etc. So it's kind of alternating, but what's very important here is you can never end with the trailing comma because we're parsing JSON after all, unfortunately. Yeah, so this takes care of that. I believe with the previous, let's say, implementations that I've described, the chain, etc., you should be able to implement that by hand. And then we expect a literal closing the array, and it's all in a chain, so it has to happen in sequence. It turns out, and one more extra thing, because look at that. We're using value here, right? And this as well might be this value. So, although to be frank, this can exhaust the stack, for example, or maybe you would need to box if this is very same thing. I'll show you later what I mean by that. But basically, we have all the building blocks, right? When we're parsing array, we want to parse also the very same thing. So maybe array has an array in itself, etc. So it all composes nicely. Yeah. Yes, it will, because the separated can also expect no input, basically. But this is, let's say, implementation detail of this parser combinator, and typically the libraries also let you specify, like separated at least one, etc. But that's a great question, thank you. Yeah, so we have arrays, pretty easy, and now for objects, which to me, frankly, at the beginning were the most daunting. But if you break it apart, it's actually just opening and closing brackets, and then you have the same, separated, but inside you just have members separated by a comma. And what is an object member? It's just a string, a literal colon, right? And a value, which can be anything. Although this string, because we implemented string in such a way that it expects the opening, closing quotes, etc. So it should just work. And there we go. We are now able to parse the whole of JSON, hopefully. although there are some additional details to that, I'm gonna be honest with you, but that basically boils down to how is this library used. So it's not so easy to call this value function from itself, because in the end what we're getting is we're composing all of those structs together, right? Alt is a struct, null is a struct, etc. And then those arrays and objects, they are also structs, and we cannot just at compile time come up with indeterminate amount of nesting. So what would happen realistically is we could implement a parser that skips over array. It would match on the opening square bracket and then skip the input with take. This is useful because in the very end, I don't know if you remember, because for sure I've lost along the way, we want to extract the stop ID from the stop name from the JSON, right? So how would we do that? We would just describe that we want to have an object which should have a member, which should be array, which should have an object. So we're gonna be doing this nesting ourselves. And for each of the values we don't care about, we can have a very similar parser that, as I said, just skips over them. So for the nested ones, it just looks for the brackets. Okay, so yeah, coming back to the JSON structure, this is my algorithm. I want to extract it. And this is the, let's say, end state. This is the parser that is able to successfully extract the stop ID of Galeria Bałtycka. Although it's not my stop name, I anonymized it. Yeah, so this is the syntax I came up with. I came up with additional parser combinators that just accept another additional parsers, giving you some niceties, like object with stops means look through the object, skip over anything that is not stops, and if you find stops, try this parser. Then array with is the same, so try each array member with this parser. And inside of that, I'm looking for an object, right? So this is this one. And this is the fun part. Although I believe I won't have the time to tell you about it. You can check out the code on GitLab. I have made a parser combinator that is only successful if all of the subsequent parser are also successful kind of in parallel. So I just try them out. If they work ever, I just keep it in a bit field. Yeah, so this one tripped, let's say. And then I maybe perhaps in the very same objects stumble upon stop ID. And then I remember this fact. And the parser for that is also, it can be any number, and I want to extract it into the buffer. And then when it all finishes, so let's say I'm finishing parsing this object, this callback triggers. In this callback, I just parse whatever is in the buffer, because buffer is just simple bytes, let's say, or chars actually. I parse it into an int. And after this all goes through, I just get my ID, and it works. And I believe it's great in this way that it's almost readable. It was great fun implementing that. And it's all from kind of simple behaviors. You get this emergent complexity that you are now able to parse JSON easily. And it just works. So that was fantastic. Although along the way, I've made some mistakes, or let's say I've learned a few lessons. First one I already touched upon. So instead of the structs, I was nesting closures. And you can imagine even here, right? So even this member parser, right? It would be a closure. It would expect this separated, let's say literal would be a closure. Then value that can be member is also a closure, etc. So it really skyrocketed. It basically didn't compile. I was just wondering what happened. Did I encounter an infinite loop in Rust compiler? Impossible, right? And yeah, it was impossible. It just took really long time, about half an hour or something, for just this, right? So this little piece of code. Yeah, so using structs is faster. At the same time, I was thinking about the stack space, because my first iteration, let's say, I was successful in extracting the stop ID with a little bit different approach that I described here. But it turns out now my parser used more stack space than the JSON itself. So back to square one. And it was because I thought to make it, you know, really kind of intelligent. So I wanted to each of the parsers to know everything. Like they stopped parsing literal, I stopped at R in true, give me some more input, I'll just start when I pick up where I left off. And this turned out to be really tricky because the whole state, as with the closures, I deeply nested, it skyrockets. So I avoid all state that I can. The only pieces of state that you found are in the combinators like chain or alt, because they really do need to know which was the parser that they last touched, let's say, or used. But I also think that this is very same stuff you would implement by your hand, right? So if you were to write a JSON parser from scratch, you would also keep some kind of state. So I thought literal uses 8 bytes, but it's actually 16, right? It's pointer and length. So I thought, maybe I can use a macro to just ad hoc create new literals that are kind of baked into the functions. So you can see them here, right? I have a lit macro. So yeah, I just did that. So whenever you use lit, it creates a new struct, which is the same as the literal we just saw, with the only difference is that the difference is now the literal is now the constant, right? So you pay the cost of having additional functions, but you don't pay for the stack space. It's just baked in. At the same time, very similar story, take at least used 8 bytes because I was using 8 bytes to describe how many of those characters we first have to encounter to understand that the parsing was successful. So yeah, I did the same thing, and now it's just a const. Although this did not have to be a macro, it can be a const generic I think it's called. And the last thing that was really bothering me is the usability of it. I mean, sorry, readability, because this was just making me pull my hair out of my head and there is not much left, right? So I thought maybe we can have some kind of nice trait helping us wrap it a little bit to, instead of having composing functions, we could be chaining them by having methods on the parsers themselves. And it's actually really simple to do. We have to create a new trait that lets us create something into parser, and we can implement it for anything we want. So for example, simple string can be turned into literal parser, for example. Or a tuple of parsers can be turned into chain. So it's really useful and improves the readability. And at the same time, to have the helper methods, we can create another trait into parser ext, I called it, extensions. And those very same methods are just calling the easy-to-use functions we just were composing some time ago. And now they become methods. We just pass self to it and whatever rest of the arguments. And yeah, this makes it really easy to read. I'll just come back a little bit here. Yeah, so it's just all methods of everything. For me, it's way easier. Yeah, and the one about closures I talked about. And yeah, so my resulting parser for the specific purpose uses 200 bytes of stack space. I feel like it's more than I would use if handwriting my own parser, but the simplicity and let's say how flexible it is, I think is worth it. And it fits on Raspberry Pico and it parses the JSON successfully. But there's more things to do as always. So basically, I want to implement a ring buffer to supporting the input trait, which would basically be the main data structure backing up the whole process, because it's very simple and efficient in terms of I can ask for more data, fill the ring buffer, and discarding the data is just pushing the pointer, right? Or sorry, the index. And that would actually fuel all of that. And at the same time, I thought, I have some tests written down, right? And they helped me a lot along the way. But I would like to create an exhaustive test for parser. Because what I'm really worried about is maybe I didn't think of something, like maybe the parser combinators work how I test them and how I tried it out. But maybe in some specific combination, in some specific, let's say for some specific input, so missing at exactly the wrong spot, it just blows up, perhaps. So what I want to do is to test a bunch of combinators exhaustively. By that I mean I will first break up the input at the first byte, then at the second, and kind of see how it goes. Ideally, it should all just work the same. Yeah, and then put it all together, stick it on my fridge, and make use of it. So yeah, that's all, and hope you enjoyed it. This is my short story about parsing.